Okay, welcome everyone to this week's Riot Science Club. So let's start with a little bit of admin. So 2 things to know about me. My name is Olivia and I'm one of the co-organizers for the Riot Science Club. The second thing is that my internet is a little bit fickle, so if it does drop, we have Marion on standby today to help out. So apologies in advance if anything goes wrong. We have a few events coming up that I wanted to highlight to you. So you can see on the slide now our kind of classic Thursday riots talks. And we also have this special event with that is co-organized by Reproducibility, the Crick Institute, and the Riot Science Club. And this is a free online event about the cost of correcting bad science, and it will take place in the afternoon of the 8th of July, which is a Wednesday. So do mark that date in your calendar because it does look like an amazing event. I'll go back to this one. So I also wanted to take this moment to say a huge thank you to everyone who attended the King's Open Research Conference last week. For those who have missed it, the recordings are now being uploaded to our YouTube channel, and you can also view them on our website, so do check those out. I also wanted to thank everyone who helped organizing the event and give a big shout out to Sam and Marion for leading on that. It was an amazing event and you've done such a good job. I have no words anymore. I say it so many times, so I shall stop. And yeah, let's move on to our speaker today. So today with us is Dr. Matt Wall. So Matt has completed his PhD at Cambridge, after which he undertook postdoc positions at Royal Holloway and UCL. From academia, he moved into industry and is currently working for Invicro, which is a company specializing in medical imaging. Throughout his career, Matt worked within many fields of psychology, neuropharmacology, and cognitive neuroscience, but the common theme across all those projects and all those fields was the use of fMRI, and that's what he's going to talk about today. So Matt's talk is about reliability in fMRI research. So over to you, Matt.
Matt,
sorry,
muted.
Yeah, we can hear you now.
I couldn't find the mute button. Right. Okay, so I'm going to try sharing my screen then. How's that look? Can we see that?
Yeah, that's perfect.
Good, yes.
Yeah. Okay, so as Olivia said, I work for this company called Invicro, and I did one of these Riot Club talks before, and I said this then, but I'll say it again now because it's funny. I feel like a bit of a hypocrite when I do kind of these talks to the Riot Club because, you know, you're all about open science and all that stuff, and I work for a big evil corporation. My work kind of gets divided between 2 bits really. So there's the, you know, the commercial work that I do with Invicro, which really tends not to be very open and you know, conforming to those good principles of open science and so on. And then there's all the other academic work that I do with students from Imperial College and various other, you know, collaborative groups from Imperial College. And in that work, I kind of try to compensate for that and try to make it as open and as good as possible. So I prefer if you know, maybe you think of me as a hypocrite, maybe you think of me as somebody who's trying to change the system from the inside, whatever you prefer. I'm doing my best. So today I'm going to present some work that was done partly by some really lovely and excellent MSc students that I had from Imperial last year, and they were JJ Lee, Sophie Yang, and Daniel Solomons. Also by 2 of my colleagues at Invicro who helped out a lot with it. Licia, who's subsequently left us and gone for a postdoc in Oxford, unfortunately, and Natalie, who's still with me. And my favourite picture of Natalie is this one from last week. This was when we were doing one of our first scans that we've done since the start of the pandemic. We're just about starting to get back into it and start doing scans at Invicro with a lot of safety measures, as you can see. But that's good. That's a good thing that's happening. So reliability is essentially doing the same thing twice and hopefully getting the same result. So specifically, it's doing the same thing twice to the same subject or the same group of subjects, as distinguished from replicability or reproducibility, which is doing the same thing twice to different groups of subjects. Some people distinguish between replicability and reproducibility, but they're quite close. So reliability and replicability are kind of related concepts. One is somewhat dependent on the other, although not entirely, as I hope to demonstrate. So why should we care about reliability in our studies? First of all, it's just kind of good practice. It's good to know about the kind of critical features of the tasks that we use. Second of all, it's good science. So as I said, reliability and reproducibility and replicability are all kind of related concepts. And if we want to do good, solid, reproducible science, we need to care about these things. Kind of a bit more into the future, you know, if an aim of neuroimaging, a broad aim of neuroimaging, is to try and develop things that will be diagnostic, measures that will be diagnostic or biomarkers of certain diseases or conditions, reliability is a key component of that kind of endeavour. You know, biomarker development is something that my company in particular is extremely interested in, as are a lot of people trying to develop imaging-based biomarkers of diseases or other conditions. And, you know, you think about diagnostic tests, they have to be reliable, they have to work every time, they have to give you a solid result with, you know, the minimum number of false negatives and false positives that you can get. When you're thinking about pharmacological fMRI, which is most of what I do, the basic design that tends to be used is something like this. So you have one visit where you give people an active drug, you put people in the scanner, you do some kind of task with them, looking at faces in this instance, and you measure some kind of response and quantify it. Then you do exactly the same thing, but with a placebo drug or placebo treatment, and you hopefully get some kind of difference in the response. And then you have to interpret that difference. So the difference that you get is likely to be some, ideally some, you know, kind of drug effect, but also some kind of noise or variability related to the, you know, the error bars on that effect. Okay, so it's really the noise part of that I'm interested in talking about today. And I want to start off by making a really kind of trivial point, actually, that fMRI is, in a kind of colloquial sense, a general sense, it can be extremely reliable. So this is an image from an old paper of mine, where we were doing kind of individual subject analyses, looking at particular sub-regions of the visual cortex, regions that are responsive to visual motion, called MT and MST. You can put people in a scanner, excuse me, do this very particular kind of visual localizer scan on them, and you can define this area, these two areas, very reliably across all these different 7 subjects on the bottom row here. We did the same thing in another study where we were defining a particular bit of the parietal lobe to use in a motor task. And this last image is from one of Fedorenko's papers, where she's looking at individual maps of the left hemisphere language areas, and you know, it was broadly similar. And of course this is true because brains are reasonably similar. Excuse me. Everybody, you know, at a kind of gross spatial scale, everybody has their frontal lobe at the front and their temporal lobes at the sides and their occipital lobe at the back. And also localization of functions are reasonably consistent. Most people activate the same areas for the same functions. And if this has to be true, otherwise everything that we're doing here with group level statistics and so on wouldn't work. So it's a trivial point, but at least in this sense, fMRI can be reliable. And you can do these kind of localizer tasks on pretty much anybody. You know, this will work all day, every day. If you put somebody in a scanner and you show them a visual stimulus, their occipital cortex is going to light up reliably. It gets a bit trickier when you start talking about cross-session and cross-subject and cross-scan reliability. So this is for, a figure from an MRI study that I did with Olivia. It was actually Olivia's first study. There she is. First fMRI study anyway. And in this study, we were comparing some different acquisition sequences, different multiband sequences, doesn't matter. But the point was that we scanned, we did the same task 6 times on a group of subjects. So the rows here are the same task scanned 6 times. We also did it on 2 different scanners, so they had it 6 times on 2 scanners, 12 times in total. They were really, really bored by the end of this. And it was a simple task that involved visual and auditory and some other components. And you see the visual activation in yellow is pretty consistent across the different scans within each session, and also pretty consistent you know, across the 2 sessions, across the 2 scanners. Same with the auditory activity in red there, and some of the others are more or less consistent. But you know, just eyeballing the gross group level activation maps, you get some pretty consistent effects. So you know, that's pretty good. Same is true for resting state data. So again, similar setup here. It was only 3 times, but we did it on 2 scanners as well, looking at the default mode network and the salience network. Default mode in red, the salience in blue. And again, you get pretty consistent looking maps across the 3 scans, and you get pretty consistent maps across the 2 different scanners. So in this sense, at least, fMRI is pretty reliable. If you start digging a bit deeper into those kind of group level statistics, it starts getting a little messier. So this was from another paper I did with a student a while ago. Similar kind of task. So we had auditory, motor, and visual and an eye movement task. And again, we did it in 2 sessions. So auditory 1 is session 1, auditory 2 is session 2, and so on. And the grey bars in the background there are the group means. And you can see they're pretty stable across the 2 sessions. And this was not a huge group of subjects. This was like 15 subjects. So even with that smaller group, you get pretty stable group level means. Not so much there, but generally. But you know, looking at the individual subject level responses, which are the coloured dots, you can see that it's a complete mess. So some subjects go up, some subjects go down, some subjects stay more or less the same. And that's the kind of thing that we want to focus on today. So what's causing these sources of variability? Well, there's lots of ideas that we could have about that. So it might be head movement. They're moving their heads in different ways in the 2 sessions. It could be some kind of physiological factor, changes in blood pressure, heart rate, cerebral blood flow, whatever. It could be other subject-related effects, so fatigue. Maybe they got a really bad hangover on 1 session, which is not, you know, unlikely with scanning students. Maybe they're in a bad mood. Maybe they just had a big cup of coffee before the scan. Yeah, you could make up any number of things that fit into that category. There's a certain amount of technological noise, scanner-related noise, so scanner thermal noise, which is just a general kind of background thing, particular artifacts, signal dropouts, magnetic susceptibility. I've called this neurocognitive variability, and what I mean is basically different strategies for doing the tasks on different sessions. And then a final catch-all strategy, which is just humans being humans, you know, humans having complex inner mental lives and thinking about what they're going to have for dinner that night, you know, during the scan, or, you know, being distracted at a crucial point, or, you know, whatever. Humans are very dirty test tubes, as Sophie Scott likes to say, which I've nicked from her. Can we try and measure some of these sources of variability? Well, Chris Gorgolewski and Cyril Pernay in Edinburgh tried to do that. Well, did that. So if you look at this column here, what they found was that for this is kind of individual subject level type analyses. What they found was that the particular kind of task that people were doing accounted for about 30% of the variance, 31%. The scanner noise was about 12%. Head movement was actually quite almost nothing, 0.5%. But head movement related with the stimulus was pretty significant, was around 18%. And then other interactions of the task and the stimulus and the head movement. And co-registration error was a very small percentage. So that's interesting. That's helping us get a bit more of a handle on exactly what sources of variance are. How do we measure reliability? So one really common and popular way of measuring is the ICC, which is the intra-class correlation coefficient. And it has a range from 0 to 1, and it's a measurement of agreement or consistency across multiple measures or ratings of the same thing. And it expresses the between subjects variance as a proportion of the total variance, so the within and between subjects variance. So if you think about that, it's if you're within subjects variance, that is the variance across your two scanning sessions in this case, is 0, then you're dividing the between subjects variance by the between subjects variance, which is the same number, and that's going to give you an ICC of 1, which is perfect agreement, because your within subjects variance is 0. Your subjects are behaving exactly the same in session 1 and session 2. If your within subjects variance is more than 0, which, you know, obviously it's going to be, then you're dividing the between subjects variance by a bigger number, because you're adding in the within subjects variance, and that means your ICC is going to be less than 1. So it's a measure of individual subject level variability, kind of, because it also includes this element of the between subjects variability, and that's because it's kind of couched within the general kind of ANOVA framework. So it does these kind of mixed effects type, it counts for these mixed effects. And the most common variants, there's lots of different variants of ICC depending on exactly your experimental design setup, but the most common one is ICC 3.1, which is a mixed models, meaning it has this within and between subjects variance with one rater, which is the scanner, because you're measuring something twice, but you're using the same thing to measure it each time, which is the scanner. Right? How do we interpret them? There's, you know, there's no hard and fast rules, but the two papers that tend to get cited the most are Cicchetti from 1994, and he said that anything below 0.4 was poor, 0.4 to 0.75 was fair or good, anything above 0.75 is excellent. Another more recent paper, which has about 3,500 citations since 2016, and it's in this terrible crap Journal of Chiropractic Medicine journal, and these two guys are chiropractors from New York. I wouldn't normally cite chiropractors in a talk because they're just, well, chiropractors, but anyway, it's got so many citations I kind of couldn't not. So they say anything below 0.5 is poor, anything below 0.75 is moderate, and they reserve anything above 0.9 for excellent. I think they're being a bit ambitious, frankly, but they're chiropractors, what do they know? How do you calculate ICCs? So you can do it with group level voxel-wise maps, and there's a nice toolbox available from a study by Mittal and various other people a while ago. So this is an image from a previous paper where I did that. This is a little working memory task. So this on the left in the red, yellow colors is the activation map, and in the green here is the ICC map. And you can see that the ICCs pretty much line up okay with the activation clusters, showing that the areas that are most activated are also the most reliable, but there are some differences. So you get this region popping up in the ICC map, which is not really there at all in the activation map, and there are a few others as well. Like this region here is in the ICC map, but not really active in the activation map. I'll come back to why that might be a bit later. The other way of doing it is kind of conceptually a bit simpler, and you can just define some ROIs however you want to. We've got a nice amygdala ROI here. You can pull out some numbers, some response amplitude data from your fMRI data for your 2 visits and your however many subjects you've got, and then you can perform an ICC calculation in your favorite software of choice. So how does it stack up? What have people done with it before? So I was really pleased when I was thinking about this talk to see a paper that was published about, I think it was about literally like 2 weeks ago, maybe 3 weeks ago, where they just presented some really nice looking new data on this. So that was great. This is bang up to date. So their title was, what's the retest reliability of common task functional MRI measures? And they did 2 things. They did some new analyses of some old data, and they did a meta-analysis. So they analyzed data from 2 big projects, the Human Connectome project and this other study called the Denoising study, which seems to be using similar tasks to the Human Connectome project. And what they found in all of these, for all of these different ROIs, is that generally ICCs are pretty poor. So you get ICCs of around 0.2, 0.3, 0.4 if you're lucky. There's a few struggling up there to about 0.6, but not very good. As a comparison, they did some analysis of structural MRI measures and found that you actually get really quite excellent reliability from structural MRI measures. So it's not that MRI per se is showing these poor reliability measures, because structural measures are fine. It's the functional measures that aren't a problem. They also did, in this paper, a nice meta-analysis of previous studies that have reported ICCs, and to zoom in on the bottom there, they found the mean ICC of all of these 56 previous studies that was reported was just under 0.4. So that's just under the the fair cutoff and into the poor side. So not great. Another meta-analysis from last year where they looked at resting state data, they found an even worse result, 0.29. So this is not great. How does it stack up against other things? So this paper from last year by excuse me, sorry, by Enkavi, where they did a meta-analysis and some new data on cognitive tasks and some survey questionnaires. So they found in their meta-analysis on previous published work, they found that tasks had an average of 0.61 and questionnaire surveys was 0.71. In their new data, they analysed tasks had a much lower value and surveys had a higher value. Now, they suspect that the higher value of the tasks from the previous published literature is maybe some result of publication bias, and that tasks might be down around this value. Another paper from 2018 looked at a load of kind of classic psychology tasks. So they had a Stroop, they had a go, no go, they had the Erickson flanker task, the stop signal task, and in their ICCs, they found some good results, but also some others that are around 0.3, 0.4. Generally, I mean, it varies. It's variable, but you do get some, fairly reliable above 0.7 or even some 0.8s there. Is the ICC a good measure? So Chris Gogolewski and colleagues say that it's not. It's certainly a popular one. Is it a good one? I don't know. So remember that you're dividing the between subjects variance over the within plus between subjects variance. What that means is that it's influenced by the between subjects variance as well as the within subjects variance. So the within subjects variance is what you care about. In this case, we're looking at the differences between the two subjects on the two sessions. But you also have this influence of the between subjects variance. So if you have if you're comparing two different studies where you've done this, it's possible that if you have the same within subjects variance, tasks that have a higher between subjects variance will have a higher ICC. And what that means is it's maybe not that great as a metric for group level studies. So in group level studies, what you really want to do generally is minimize the between subjects variance. And that gives you nice, strong, robust, reliable, significant results. It's possible that if you were picking your task for your group level study on the basis of your ICC, you might pick one that has a really high ICC, but that might reflect the fact that it has high between subjects variance, which would actually make it not a good candidate for your group level study. I hope that makes sense to people. But nevertheless, people use it. It's probably the most popular measure that people use. There is one other one that I want to talk about, though, which are dice coefficients. And these are much more simple. So Sorensen dice coefficients, sorry, to give them the correct name and the correct credit. They were described independently by two different people around the same time. This is a really simple calculation. So it's about measuring overlap between two sets, right? And which makes it a good measure for fMRI data because you have these spatial maps. Again, the range is 0 to 1, and it's just applied really strictly at the group level. I mean, you could apply it at the individual level, but most people seem to apply it at the group level. And it's really simple. It's the intersection, so the overlap between your two things, x and y, multiplied by 2, and then divided by the total. So you can think of it a bit like the overlap of a Venn diagram, okay? If you want to calculate the overlap of that, a little bit of topical politics for you there. So that's nice and simple, and that appeals to me because I'm a simple person. So for the rest of the talk, I'm going to talk about some new data that we've got, which is trying to look at this kind of stuff. This is the data that was collected by the MSc students and Lucia and Natalie. The aims of this really were to try and take some of the tasks that we use quite a lot. We tend to use often quite similar tasks across different projects. So we thought it'd be nice to try and characterize the reliability of these tasks that we rely on. Secondly, our spin on it. A lot of people have tried to characterize the reliability of these different various tasks. Our kind of new spin on it was, well, let's try and explore the effects of different denoising pipelines. So the idea with this was, well, if you can reduce the effect of some of those sources of variability, if you can get rid of some of the noise out of the data, will that give us higher reliability metrics? Will that improve things? Intuitively, you might think that might be the case if it's those noise signals that are causing the problem. And we also did all of this as well for the resting state data, but I'm not going to show it today because it's just too much data. So that's for another talk. The general methods were, we had 25 subjects, we scanned them on 2 separate occasions with about a week or 2 in between. We used the same scanner, Siemens Trio with 30-channel head coil. We had a nice fast multi-band acquisition, 1.25 seconds TR, nice whole brain acquisition with 3mm slices. And we did all the analysis, pretty much all the analysis in FSL. And pretty standard pre-processing, although I'll talk a bit more about that in a second. Motion correction, temporal filtering, 6mm smoothing, and registration to the MNI 152 template. All the analysis was done with the feet module in FSL, and the group level analysis used a threshold of 3.1, or P is less than 0.5 cluster corrected, which is pretty conservative, pretty tough. Okay, so there's a lot of brains coming up. Before that, I need to talk about the tasks. So the tasks that we used were a go, no-go task, a really simple implementation. They just saw a G or an N on the screen. When they had to, when they saw a G, they had to push a button. When they saw an N, they had to inhibit themselves from pushing the button. So 2 conditions, go and no-go. We did an emotional images task. So we had neutral, positive, and negative images. That was a block design. So they saw 5 or 6 images in a block with a few seconds each, and they were rating them as to how positive or negative they were. And the negative ones we used weren't like really negative. They were kind of moderately negative and fairly positive. We had an implementation of the NBAC working memory task, which is a spatial version of that. So markers could appear on the screen at any one of 6 locations, and the sequence that they had to remember was related to the position of the marker on the screen. And we did this because a lot of people find that, well, people, mostly young kind of people, the students that we were scanning, and find the standard NBAC with letters or something relatively easy. People get quite close to kind of ceiling levels of performance, but people tend to find the spatial one a bit harder. And again, a really simple implementation of the NBAC, just 2 conditions. We had a 0 back condition where they just had to say whether it was the marker was at 12 o'clock or not. So they don't have to remember anything there really. And then the 2 back condition where they have to remember the last 2 locations in the sequence. And finally, we had a version of the monetary incentive delay task. Again, a really simple implementation with no losing trials or anything like that you often get with the MID task. So this is a task, for those that aren't familiar, that's designed to activate the reward systems of the brain. So they were winning money on this task. They could win up to about 20 quid, I think, if they performed perfectly. And there were just 2 conditions, win neutral, depending on what coloured square they get at the beginning. If it's blue, they know they can win money on that trial. If it was orange, then they know they can't win any money on that trial, but they still have to respond as fast as they can. And you compare win and neutral to see an anticipatory reward activation. So those are the tasks. We deliberately developed some really quite simple versions of all of them in order to, you know, try and essentially maximize the reliability. So they're all pretty simple. And then moving on to the different analysis options that we tried. So the basic version was kind of no extra denoising at all, except for we included the 6 head motion regressors in the first level analysis models. Then we used something called ICA aroma, which is independent components analysis, automatic removal of motion artifacts. So this is a nice bit of software that does an ICA analysis on each individual subject's data. It kind of automatically identifies components that it thinks are related to head movement. It filters them out of the data, and then you, in theory, you have a nice clean set of data you can do your final analysis with. Kind of similar to that, but a lot more labour intensive. We did a manual ICA denoising as well. So this is exactly the same idea. You do an ICA analysis, but then you have your poor long-suffering MSc students sit there and look through all of the components for all of the tasks and identify the ones that they think are noise, identify the head movement related components plus other noise components that you get, like related to, you know, vascular effects and various other things, manually, and then you manually filter those out of the data prior to your final analysis. So in theory, ICA aroma is just focused on head movement related effects because they're relatively easy to identify. Manual ICA should be removing similar head motion components to the ICA aroma, but also other noise components that are a bit harder to identify in an automatic way. Then the final one we did was something we call mean signal regression. So this is where you segment the anatomical images into grey, white matter, and CSF, and you take the mean signal from the functional data from the white matter and the CSF, and you include that in the analysis models as confound regressors. And the idea there is that you shouldn't be seeing any bold activation in the white matter, and you certainly shouldn't be seeing it in the CSF. So any fluctuations you do see in those areas are likely to be just noise, or mostly noise. So if you include those regressors in the analysis models, that should, in theory, clean up your data. So there's a lot of brains coming up, and I'm not going to go through all of them and talk about all of them because, well, life's too short, and so is this talk. But I'm going to skip through them fairly quickly and just talk about some salient points. So this is the go, no-go task. We saw some nice activation in the anterior insular and in the dorsal anterior cingulate, which are very kind of inhibitory areas. That's like a classic thing. The mean signal regression worked really well for this task in that it showed us a lot of extra effects. Sorry, I should have said, for each analysis pipeline here, we've got on the left-hand side, we've got the activation map in red and yellow, and on the right-hand side, we've got a voxel-wise ICC map in this kind of blue cyan color. Yeah, so that's the go, no-go task. If I zoom into one of those, so this is just the basic denoising pipeline. So you can see, just eyeballing the ICC maps, you get reliable results in, you know, the anterior insular in some similar areas. You also get a lot of other stuff, including some, you know, some really big clusters in areas which are, you know, clearly not activated at all in the standard analysis, which is interesting. So I'll come back to that later. For the emotional images task, we saw obviously lots of activity in the visual cortex. And again, the mean signal regression seemed to help with that. So actually, again, for reasons of time, I'm just presenting a single contrast in that task. We had negative images as well. I'm just showing you positive over neutral. The mean signal regression here actually really helped. And we got this nice activation cluster in the medial frontal lobe, which often shows up in kind of people looking at positive things. It showed up a little bit in the basic one, but the mean signal regression kind of brought it out very nicely. For the NBAC, the NBAC always gives you very strong, robust results, and it did here as well. You can't see a lot of difference across the different denoising pipelines. And the NBAC, I'm going to zoom into one of those again. The NBAC probably gave us the best looking, again, just based on eyeballing the data, the best looking correspondence or localization between the ICC maps and the activation maps. So you get similar areas, but even here you still get other areas showing up on the ICC maps which don't show up on the activation maps. Finally, the MID. So with the MID, you get a lot of activity in the striatum, and that's what we've got, as well as a lot of preparatory motor activity, and that's what we've got as well, and some visual stuff. Interestingly, the mean signal regression kind of killed that, which, yeah, that was hard to interpret. Anyway, just a brief kind of digression about that phenomena where you get high ICC values, meaning that the brain data are very reliable, but without kind of co-localized activation. Why should highly reliable values appear where there are no significant activation clusters? So the paper from Sarah et al, where they first did these voxel-wise ICC maps, their explanation was that regions might be responding consistently to the task, but in a non-linear way, or just in some way that doesn't fit the standard statistical model that's being used in the task, which is based on the standard hemodynamic response function. Now that's a really interesting idea. And again, maybe I'll come back to that in a minute. But the idea that some brain areas are responding in a different way that we don't really know about is really interesting. Alternatively, it could just be all an artifact. So people might be moving their heads in consistent ways across the two sessions. Possible. It could be signals from draining veins. It could be some scanner-related issue, like one of your coil elements is a bit shonky and it's not performing correctly. Some interaction between head motion and susceptibility dropout, and that kind of thing. Anything that could be replicated across the two sessions could produce those effects. So then we did. Then we did the other way of looking at ICCs, which is to look at ROIs, and we defined our ROIs using some meta-analytic data that we downloaded from Neuroscience. If you don't know Neuroscience, you should check it out. It's a great website. You can download all kinds of fun stuff from there. So these are the meta-analytic maps that we got from Neuroscience for our 4 tasks. And those are the ROIs that we used. The ICCs that we got, pretty poor overall, I mean, I have to say. So our 4 tasks on the rows and our 4 analysis options in the columns. The NBAC was the only one that showed reasonable numbers. I mean, these are pretty good. These are not so great. The emotional images maybe just hovering around the boundary of poor to okay. The others, definitely poor. And I mean, I was kind of expecting this, I have to say. I was expecting that the tasks weren't going to show great ICCs. What I was more hopeful about was the effect of the different analysis options. But in fact, I mean, if you look across the columns for each of the tasks, there's really not a great deal of difference. The ICA aroma seems to really knock down the NBAC value. But apart from that, I mean, there's really not a great deal of difference across these different analysis pipelines, showing that these denoising options are really not having a great deal of effect on, at least on this particular reliability measure. So that was a disappointment. Then we looked at the dice coefficients, the other way you can look at group level reliability. Sorry, excuse me. So just as a reminder, this is the activation map from visit 1 and visit 2 of one of the NBAC analyses, visit 1 in red, visit 2 in green, and we're quantifying the overlap between the two. And these are the numbers. So again, the NBAC performs really well. Interestingly, we get a really nice overlap for the emotional images as well, around high 0.6s, 0.7s. And again, but unfortunately, the other two still, I mean, better maybe, but still fairly poor. Kind of interestingly, if you do this, analysis looking at different contrasts, so if you compare the task conditions to the baseline, you get much better results. So this is just an example of the MID. So when you compare the two task conditions, which is generally what you want to do, neutral is your control condition, green is your experimental condition, you get poor numbers. You do get better numbers when you look at the task conditions in isolation, but that feels a little bit like cheating to me, but I thought it was worth mentioning. Even more disappointingly, the numbers that you get from the kind of the basic denoising option are actually some of the highest. So, okay, not quite the highest for the go no go, but certainly higher than some of the other denoising options. It's the highest for the emotional images, it's the highest or joint highest for the NBAC, and it's the highest for the MID. So the denoising options are more or less actively hurting you. So a little bit of a summary. I'm really running out of time. I've got just a couple more slides. I'll go through them fast. So what have we learned? Doing reliable fMRI studies is hard. Even with these, really quite simple implementations of these common tasks, we're not showing really good reliability numbers. ICCs are pretty poor, except for the NBAC. They're actually, fairly comparable with previous reports, 0.3, 0.4, it's that kind of thing. DICE coefficients are a bit better. The denoising pipelines had really not a great deal of coherent effect. And I need to dig into this data a little bit more and try and figure out what's going on here. It could be something to do with their effects on within and between subjects variance, because remember the ICC is dependent on both of those things. So they may be having some effect, but they may be having no net effect on ICC values, if you like. And then clearly they're having some kind of effect, because we saw it in the activation maps. For some of the tasks, at least, they differ in the activation maps, but they're having no net effect on the ICC values. And poor individual level metrics don't necessarily mean poor group level metrics. So we saw in the emotion task, it had relatively pretty poor ICC values, but they're much better DICE coefficients when you look just looking at the group level maps. A couple of final things, kind of more theoretical, conceptual points to finish on. Does variability matter? So this very recent paper out a couple of weeks ago cites Lee Cronbach from 1957, where he was talking about two different disciplines in psychology. And the experimental discipline is all about looking at human universals and doing group level averaging. And in that, from that perspective, individual variation is a problem. It's an error that must be minimized. And then there's the correlational discipline, or what he called the correlational discipline, which tries to look at individual differences. So I mean, a lot of personality research might fall into this kind of group. So it tries to explain variation between people by measuring how they differ, and there the variance is not an error to be minimized, it's actually the main parameter of interest. And I think it's fair to say that most fMRI research comes from that experimental perspective, and tries to minimize between subject variance. But if we're serious about what I call translational efforts, which is, you know, trying to develop imaging biomarkers, trying to do diagnostics, maybe look at patient stratification, that kind of thing, we're going to have to start looking at these individual differences seriously at some point. And reasons to be cheerful, I've called this slide, I can't remember why. Oh yeah, that's why. There was a nice paper from 2012 about this, which was a kind of fairly jokey little summary, that was called Test-Retest Reliability in fMRI, or How I Learned to Stop Worrying and Love the Variability. And the point they made here was that variability might actually be a rich source of information. So people thought up until relatively recently that the spontaneous fluctuations in brain function that you see were just noise, and then people decided that they were actually really interesting, and resting state networks were defined. People realized that the noise was non-random and spatially localized and so on. And this whole explosion in resting state research came along. And they also, McGonigal in this paper also made the point that most fMRI studies still use fairly simple linear models to analyze their data. And there must be all kinds of non-linear things going on in the brain that we may be missing. And some of these sources of variability might turn out to be coherent responses, just maybe non-linear ones. Another similar kind of paper making similar points, variability in brain activity, a nuisance or an opportunity. So they make the point here that variation might be due to genetics, might be due to white matter organization, cognition, behavioral variability, all kinds of things. And they also say that multimodal approaches may help. So to understand this variability, we might have to bring in things from genetics. We might have to do some DTI scans to look at the white matter organization. We might have to do some better cognitive testing. Maybe we might have to look at PET data to look at, you know, underlying neurochemical factors, which might help to explain the variability that we see with fMRI tasks. Maybe we want to do some EEG. And try and figure it out. And to address that earlier point about the fMRI studies only tend to use simple linear models, well, of course, that's not true. These days, there are all kinds of machine learning applications going on, and something deep learning networks. They're going to change everything. Practical things. What can we do? This is the last slide. I'm nearly out of time, sorry. I'll run through them really fast. So first of all, you can look at and report reliability metrics for your data. That's a good thing to do. If you have data that have 2 sessions, do that. Why not? We can improve reliability by generally getting more data. So more subjects and more data from each subject. So doing longer scans, more task sessions. We can try and develop new or better tasks. Now that's a tough ask. These are ordered roughly in order from easy to hard. So we're getting to the hard ones now. So, you know, I tried with these quite simple implementations to develop reliable tasks, and I, you know, mostly failed. So, but we can definitely try and develop new or better tasks. We can develop and test new or better reliability metrics. So we can try and get away from some of the problems with the ICC. Develop better analysis models. So, I mean, the machine learning guys are beavering away on that. And explore multimodal approaches, as I said in the previous slide. And finally, get funding bodies on board with all of the above. So, you know, people, it's kind of tough to put in grants where they have, you know, you have a lot of testing of reliability across sessions, because it's not, you know, people, it's kind of boring, you know, it's not doing a wonderful, exciting new task that's going to show you fabulous new things about how the brain works. but it's kind of that boring groundwork that you just kind of have to do. So be good to have more of an emphasis on this kind of thing at the funding bodies and have them giving more money to studies that use this kind of approach. And yes, that's the end. Thank you very much. So I see we've got some questions on the chat.
Yeah. Thank you, Matt. That was really interesting. So we're going to go through the questions in order of upvotes. So everyone, please do upvote the questions that you want to have asked first. So we'll start with a question from Emil. So he's saying, regarding looking at the signal in the CSF for identifying noise in the analysis, you have pulsatile flow of the CSF, which could show up as a signal fluctuation, which isn't noise. Any risk of regressing out physiology this way?
Well, yeah, but I mean, I would say in terms, I mean, it's interesting. It's an interesting signal, and the physiology behind it is interesting and complex and so on. But I'd argue that in fMRI, general fMRI task terms, physiological effects like that are generally thought of as being noise. So I mean, that's usually a signal that you want to get rid of. And there are specific approaches you can use to get rid of those kinds of physiological signals. So not just CSF pulsation, but respiratory signals and cardiac. Well, the CSF pulsation is cardiac, isn't it? So you can record cardiac and respiratory signals, and you can explicitly regress those out of the models, and a lot of people do that, particularly with resting state data. So yeah, I'd say that is noise. Sorry.
Okay, thank you. We have a comment from Mitchell. So Mitchell's saying, thanks, Matt. An important point to make about the ICC is that it really depends on the question you're asking. If your question in any way depends on the rank order of participants, such as consistency across sessions, correlations with behavior or scales, then it is very informative. Other questions may benefit from different assessments. Smiley face.
Thanks, Mitchell. Yeah, I mean, sorry, I just respond to that a little bit. Yeah, the ICC, it's kind of a weird composite measure. Yeah, and I feel like a lot of people are using it, and maybe there needs to be a bit more of a digging into it and a bit more clear understanding of what it is. Yeah, so thanks.
Okay, and now we have a super long question from Sam. So Sam is saying, two-part question. So let's start with the first part. So what lessons can we learn, if any, from the recent paper? Variability in the analysis of a single neuroimaging dataset by many teams, Botvinnik, Nezer, and colleagues. And he says training is important, but are there any core resources you could point to?
Okay. Yeah, so actually I was an author on that paper, which I was very pleased about because it got into Nature, which is amazing. So yeah, this was for those that don't know, this was a paper where it was organised by Russell Poldrak, who's going to be speaking in this slot next week, I think. So I imagine he's going to mention that then. I'm looking forward to seeing that talk. I can't imagine he wouldn't mention this next week. So this was a paper where we at 70 different analysis teams all around the world got the same set of data to work on, and we all analysed it in whatever way we wanted, and then they collated the results and looked at the agreement across different teams. So it's looking at kind of a different focus of attention on reliability. Really, it's looking at the effects of different analyses. I mean, well, we did different analyses on the data that I've shown you today as well, although I mean they're largely the same. They differ in the details, and there's a lot more variation amongst these 70 teams. I mean, what they found in that paper was that for some hypotheses there was pretty good agreement across the 70 teams, and for others less so. But I mean, you're right. It's a good point to raise. That's another source of variability that we have to fight against. And what was are there any core resources you could point to? I don't know what he means by that. Really, about analysis techniques.
I guess any kind of recommendations that people should take on.
Well, I mean, I would have a read of that paper that I just stole half of this talk from a couple of weeks ago, the Elliott et al. Paper. So they have some really good recommendations at the end of that paper. I can see the second part here.
Yeah, I'm going to read that out to you now. So according to John Roycer, the main source of variability was a subgroup of investigators who accidentally misspecified the model, thereby getting opposite results to everyone else. If they had been removed, which arguably they should, the analyses would probably have been homogeneous. Do you think this reflects a general lack of guidance of what is the best practice and ways to uphold best practices?
Right. So this is talking about that paper again. I mean, I don't mean to be annoying, but I mean, you should probably ask Russell Poldrack this next week. I think it's incredibly easy to make a mistake with fMRI analysis and make a fairly disastrous mistake. So, which I guess these teams did. Does this reflect the general lack of guidance of what is best practice? I don't think it does. I mean, I think it's relatively clear what the best practice should be for at least the kind of standard analysis that people tend to do. I mean, there's endless variations that people have come up with that be kind of at the fringes of fMRI analysis, and they may deviate from the standard. But I think the core and the core kind of general linear model type analysis is pretty well established now. I think it reflects the fact that it's still a really complicated thing to do, and you can very easily make fatal mistakes. Check your work.
Okay, thank you. So the next question is from Cyril, and it reads, "Hey Matt, how did you threshold for dice? With Chris in another paper, we showed this matters too."
Well, we just used the standard 3.1 cluster corrected p equals less than 0.05 threshold. Yeah, I mean, this, like I said at the beginning, this data is still at quite an early stage. So, you know, in Mittel's paper as well from 2009, they did this thing where they calculated ICCs based on different activation thresholds as well. And yeah, thresholding is an issue for ICCs and for DICE. I guess it'd be worth trying maybe different activation thresholds and seeing how that affects the DICE coefficients on this as well. Yeah, thank you. Okay.
Now Mittel's saying, have you thought about reliability methods that work in hyperspace?
Wow, that sounds very Star Trek. In hyperspace, so I mean, you're talking about in a high dimensional space. Well, I mean, the answer to that is no, but I mean, tell me about them sometime. That sounds.
Okay, the next question is, the lack of an effect of denoising on ICC, is that in line with, for example, head motion explaining little variance?
Again, this is something I want to try and dig into this data a bit more and try and figure out exactly why these denoising pipelines didn't have much of an effect, because I think that's an important question. Particularly if I'm going to, you know, try and publish this at some point. I think it'd be good to have at least some explanation of why they're having no effect. So, I mean, it could be a lot of things. So it could be what I mentioned in the talk, which is that the denoising pipelines are having some kind of relatively complex and interactive effects on both the within and the between subjects variance, which is meaning that because you're dividing one by the other in ICCs, it's having no net effect on the ICCs. It could be something else I just thought of, which I can't think of again. Oh, it could be. I mean, the denoising pipelines are, not perfect. So, if you're trying to identify and remove head motion related components of your data, but you have some correlation between head motion and your task or your stimulus, which is very likely, very possible, particularly if you have some kind of motor component to the task. People push a button, they move their head a little bit. So you've got some correlation between your task and head motion, and you're trying to remove the head motion components. Maybe you're also possibly eroding some of the signal that you should be getting from your task as well. So that might be part of it as well. We might be by trying to reduce head motion, we're actually eroding signal from our task, and that's affecting the reliability too. Those are my two best explanations, I think, or speculations.
Okay, thank you. The next one is, if high ICC, low activation, is an artifact, would you expect it to be similar across the whole brain?
Possibly. Maybe not if it's, if it's localized to say, if it's a signal you're getting from big draining veins or something like that, that would be more localized because they're localized. If it's head motion, maybe you'd expect to see it more around the edges or around the ventricles, a bit like you do with kind of normal head motion artifacts in activation. But yeah, maybe.
Okay. The next one is, I guess, more of a comment. There are 10 different ICCs for different questions, and the one presented is one for relative agreement. The ICC for absolute agreement would be preferable.
Okay, so okay, thanks for that. Yeah, you get consistency and then absolute agreement values when you do ICCs. So this is whether your subjects show the same pattern across the two sessions. So whether, say, they all go up, and whether from session 1 to session 2, and whether the actual values across subjects are the same. So absolute agreement would be all of your subjects have a value of 5 in session 1, and they all have a value of 10 in session 2. Then the consistency measure would be some of your subjects have a value of 5 and go up to 10, and then other subjects have a value of 10 and go up to 15, for instance. Well, I guess you could argue that either way, I'd like to say. So, you expect some global differences in activation amplitude between different subjects. And for my money, I think that's less important, at least in the kind of work that I do. We tend to be more focused on between session differences because we generally want to look at drug effects rather than global differences between subjects. But for other applications, for other questions, yeah, maybe you want to look at absolute agreement.
Okay, so we just closed the Q&A. We just have a few more questions to go through. So what are the situations where you can expect ICC and the DICE measure to be different?
Well, I've just shown you some. So, in the emotion task, the ICCs were pretty poor, and then we got reasonable looking overlaps in the DICE coefficient. So this is that thing where you're going to get robust, reliable activation if a proportion of your subjects respond well, but it might be a different proportion of your subjects in the two sessions. So it's like that. Can people still see the slides? Can I go back on the slides? Is that doable? It's like that. This situation here. where you have, you know, stable group level measures, but subjects go up and subjects go down fairly randomly. And so you're going to get pretty good agreement on the DICE coefficients with that, because you're getting good strong activation maps in both of your sessions that are going to be pretty similar. But within those group level results, your individual data across the two sessions is going to be very variable. So you're going to get a low ICC. I think that covers it.
Okay, thank you. And the last one, I believe this is about the multi-button project that you presented at the beginning of your talk.
Oh, I'll let you for that one.
So now I'll leave it to you. So basically the question is whether we can consider each of the scans as a true replication of the same scan, or whether the sequence would have made a difference, or time of day effects, or anything similar to that.
I mean, sure. I mean, that was a kind of toy example at the beginning. So the sequence actually did have some effects as you went up. You know, as you get to higher multiband levels of acceleration, up to 4 or 6, you get some drop-offs in temporal signal-to-noise ratio, which you can see if you want to go and read the paper. But yeah, I mean, yeah, you're gonna get differences in effect. So it's not a true replication, but I mean that was a kind of a fairly toy example that I just used at the beginning, mostly because it was from one of my own papers and I was familiar with it.
A really good paper.
Oh, fantastic.
Okay, thank you, Matt. That was really lovely. Okay. Thank you everyone for listening. And just to highlight, next week we have Professor Russell Poldrack, who will give a sort of follow-up talk on this. And he will be giving some recommendations on what you can do to actually improve replicability in fMRI. And just to highlight, that talk will be at 6 in the afternoon, just due to the time difference between us and him. And I think most of you who are on the mailing list should have received a calendar invite to that. So yeah, thank you everyone, and see you next week.
Thank you very much for having me.